Suppose there are 25 bacteria in a petri dish, and the number of bacteria doubles every hour. The key word in that sentence is double. So when we look at this table here, we're starting with 25 bacteria. So if we double that after an hour, we get 50 bacteria. And if we double 50, then we're going to get 100. And if we double 100, we're going to get 200 bacteria after 3 hours. And what we've been doing in this function is we've been doubling. We took 25 and we multiplied by 2. Over here, we took 50 and we multiplied by 2. We took 100 and we multiplied by 2. We want to go back on something that we learned last week. How do we write this function, or can anybody help us write this function? Well, what did we start with? We started with, Gordon? We started with 25. And what's happening to our function? We're doubling it. So there's going to be the 2. It says write a function for the number of bacteria present after T hours. So our amount is going to be 25 times 2 to the T. If you think back to our formula, we did A times B to the X. That's what we used a little bit more than a week ago. So now, once we can identify the formula, what we're going to do is we're going to go ahead and we're going to put in use your function to determine the number of bacteria after 6 hours. So now we're going to take 25, we're doubling it, but we want to know after 6 hours. So when we type that into our calculator, 25 times 2 to the 6 will give us a value of 1,600. So we get 1,600 bacteria after 6 hours. Well, now let's take a look at what we're working with here. It says use a graphing calculator to graph the function from part B. So when we go back into our calculator, if we go back into y equals, we can type this in. It's 25 times 2 to the x. Don't type in the 6. There we found the value for 6. We want to type in the function so that when we graph it, we'll get a picture. The thing is, what we're seeing in this picture is we're over here in the second quadrant, and all of these x values are negative. But what does the x-axis represent? And if we go back and we look at our table, what does the x-axis represent? It represents the time, the first value in our table. So it's going to represent time. And what we see in our calculator is we see a picture that it's all negatives, but can time be negative? Time's not negative. It seems like we never have enough of it, so sometimes we talk about negative time, but it really can't be negative. So knowing this, what would be an appropriate domain for this? Well, since we can't have negative time, let's start with 0. We can have 0 seconds. And then, in fact, we're not looking at seconds here, but we're really looking at hours because it says time in terms of hours. So we looked at the first 3 hours, but what if we went to 20 hours? And I just left my scale as 1. Well, we've seen the x-axis represents the time. The y-axis then represents the other value in our table. And the other value in our table is the number of bacteria. And the thing is, we know that we started with, in our bacteria, we started with 25. But I started back here at 0. In terms of looking at an appropriate range. Started at 0. And then we left off at 3 hours, we had 200 bacteria. But let's pick a higher number, maybe 1,000, to look at on our screen. And in terms of the scale, the Y scale, I'm going to put in the 50. You could use 100. It's not going to make any difference. We'll be able to see the picture. So if we go back here, where are we going to look at a more representative graph? Well, let's go to the window setting. And we're going to type in 0. And then I said, well, let's go to 20. And I left the scale as 1. Then I said 0 for the minimum. And we went to 1,000. And then finally I changed my scale to 50. 100 might also be a good one. But when we look at that now, we're going to get a more representative graph. And there's our picture. And we didn't actually have to do that on the problem, but we talked about what we were just looking at, so I wanted to put that in there. But if you look at that, it says, what would be an appropriate domain? X is greater than 0. What would be an appropriate range? Y is greater than 0. In terms of, again, what would be the appropriate domain? X is greater than 0. What would be an appropriate range? Y is greater than 0. Now, we have the function typed into our calculator. We want to look and see between what 2 hours the bacteria count will reach 500,000. So we're going to go to our table, second and graph. And I'm going to start back up here with what we started with originally. We had 25 bacteria, 0, 25. Well, what we're looking for is, when will we have 500,000? And I didn't really need to go backwards because we need to keep scrolling through here. And it says, between what 2 hours will we have 500,000 bacteria? So we're looking for 500,000. And we find it here between 14 and 15. Because at the 14th hour, on your table, you just saw we have 409,600. And at 15, we have 819,200. So in other words, the answer to that problem is between 14 and 15 hours. But typically, we don't want to know between. We want to know exactly when we get there. So that's what we're going to finish with on this problem here, is write an equation that can be solved to answer exactly the bacteria count. And remember what we started with. We started with 25 times 2 to the t. Well, now what we want to know is, when will that equal 500,000? And that's what we've spent our week on this week, is learning how to solve these. What's our first step on this one? Jordan? Let's divide both sides by 25. We need to isolate the variable, and moving that 25 to the other side is as much as we can do. 50,000 divided by 25 is 20,000 equals 2 to the t. Well, now this problem should look very familiar. At least the format of this problem should look really familiar, because that's what we spent our time on this week. We spent our time putting a logarithm, a common logarithm in on the left, and a common log in on the right. So we're going to get log of 20,000 equals log of 2 to the t. Now what? What? Move the t out in front. So now we've got the t. And we've got log of 20,000 equals t times log of 2. Our goal is to figure out exactly when to the nearest thousandth of an hour. So what's our last step before we can actually type it in our calculator? We can divide both sides by log of 2. And that's going to allow us to figure out our time. So it's going to be log of 20,000 close the parentheses divided by log of 2. And we get our value there. And if we round then to the nearest thousandth, we end up with our time equals 14.288 hours. Because that second 7 is what we use to determine to round. That's going to raise that 7 up to an 8. So as we flip our paper over to the other side, similar type of problem. And suppose for a particular patient and dosing regimen, a drug reaches its peak level of 300 milligrams in the bloodstream. So there's where we're going to start. For me, I always think of it as taking my allergy medicine. The first hour is the best. And then what happens is, then our drug is eliminated from the bloodstream at a rate of 20% per hour. And I know that we have a table here where we can fill it in, but maybe coming up with the function first might be able to help us make our table quicker. So the first word to note here is the eliminate. And we started with the 300 milligrams. If we eliminate, what are we doing? Is it growth or decay? It's decay. So this is going to be 1 minus, well, 20%. Remember, we're going to move the decimal point 2 spaces to the left. So it's going to be 0.20. Good. And then, let's see, write a function that gives the amount of drug in the patient's bloodstream after t hours. So we're going to have our time there. So it's a function in terms of time. And the only reason why I think that it's helpful to write this equation first is, if we go back into our calculator, and we go back into the y equals, and we type it in, we've got 300 parentheses 1 minus 0.20 to the x. If we type it in, we're going to have to type it in sometime, probably. And then we go to the table here. There's our first number, 300. Then we have 1, 240. Then we have 2, 192. Just reading it straight off the table. And 3, 153.6. And 4, 122.88. And the fifth hour, we have 98.304. So we didn't have to do a bunch of picking up our calculator and typing in and all of that stuff. We could use this function to help us come up with our value. But as we look at this now, same kinds of questions that we were looking at on the front page. It says, using the graphing calculator to graph the function, what does the x-axis represent? Well, if we go back and look at our table, what does the x-axis represent? Time. And do we need to change any time values on what we had from the last problem? Probably not. Time is still not going to be negative, so we could start with 0. And then 20, and I would leave my scale as 1. So in other words, an appropriate domain to use for our window setting will be x is greater than 0. Well, what does the y-axis represent? If we flip back and we look at our table, it's the amount of drug in the bloodstream. We'll just shorten that just a little bit. The amount in the bloodstream. And in terms of what we would put in our calculator, I still would start with 0. But what's the most that's in our bloodstream? The most that's in our bloodstream is 300. So in terms of my y value here, I'd probably do a little bit more. I'd probably go up to 500. And then in terms of the scale, I would probably still leave that 50. So even though it doesn't ask us to do that in particular, if we go back over here to our window, we only need to change one number on there. We didn't change very much from the last problem because it was still time, but we can change that 1,000 to 500. Is it still going to graph if you have the 1,000? Yep, it's still going to graph. But then this gives us a little bit of a picture here to show that we are decreasing, a decreasing function, a decay function. It says, using the table in your graphing calculator, determine how long it will take for there to be less than 10 milligrams of the drug in your bloodstream. Well, if we pull up our table now, and go to second and table, we want to look for a number less than 10. So we start scrolling. At 10 hours, we still have 32 milligrams. So we keep scrolling. At 15, we have 10.555, so we're close. At 16, we have less. So when we look at this, again, what happens is we have, at hour 15, we have 10.555 milligrams in our blood system. And at hour 16, we have less. We have 8.444. So it says, how long will it take for there to be less than 10 milligrams in there? 16 hours. And again, if any of you take allergy medicine, you've probably experienced it. If you have the 24-hour allergy medicine, at some point you notice that the amount in your bloodstream is low enough that you feel ready to take your next allergy pill. But as we finish this here, it says write an equation that you could solve to determine exactly how long it will take to have less than 10 milligrams of the drug in our bloodstream. So once again, if we think about our function, we had the 300 times the 1 minus 0.2 to the t. And what I'm going to say is let's start with equals 10. Well, when we do this here, we can simplify our function just a little bit. 10 equals 300. 1 minus 20% is 80%. So I just did 1 minus 0.20 to get the 0.8. So we have a 20% decrease. In order to solve this problem, we need to isolate the variable. We're going to divide both sides by 300. But notice, if we type in 10 divided by 300, we're going to get a big long decimal. Now we could simplify that fraction a little bit by hitting math, enter, enter. So let's simplify it, but don't shorten that decimal. Don't do 0.03 or 0.033. Don't round. So let's say that this is 1/30th, which it is, equals 0.80 to the t. 0.80 to the t. What do we have to do to solve this? Tiffany? Put log in. We're going to put log in it. Both sides. So we've got log of 1/30th equals log of 0.80 to t. Matthew, what are we going to do with that t? And I call it the front, he calls it the back. Close enough. And we're going to bring that down. So now what we have is we have log of 1/30th equals t times log of 0.8. And we want to solve for t. And it's t times the logarithm. So the inverse operation is to divide. And that's what we're going to type in our calculator. And we need to go back and look at what the problem is asking again, but this is going to get us almost to answering the question. It's going to be log of 1 divided by 30, close the parentheses, divided by log of 0.8, close the parentheses, and when we press enter, we'll get our value here. Let's move on around to the nearest thousand, and we're going to look at our fourth decimal space, which is the 1. And that means when we go to round there, we're not going to round much. We're going to get 15.242. I'm going to write the t over here on the left. So what this is it says the time at 15.242 hours, we're going to have 10 milligrams of the drug in our system. The question says on here, how long will it take to have less than 10? So if we finish this, that means that it's going to have to be more than 15.242 hours for us to have less than the amount in our bloodstream.